Today we're looking at bubble sort, probably the most famous sorting algorithm in the world, and the simplest idea you'll ever hear. Here's a messy list of numbers. Let's sort it. Look at the first two neighbors, 6 and 5. 6 is bigger, swap them, move right. 6 and 3, swap, keep going. Compare neighbors, swap if wrong. But then 6 meets 8, and 8 is bigger. 8 takes over, winning every comparison, sliding all the way to the end. The biggest number just floated to the top, like a bubble rising to the surface. That's where the name comes from. One pass, one number sorted. Pretty simple, right? But here's the thing. We sorted one number. There are still 7 left, so we go again, and again, and again. 7 passes, 28 comparisons, just for 8 numbers. What about 1,000? That's n squared, and that is terrible. So here's the real question. The worst sorting algorithm in computer science is the most famous one in the world. Why does everyone learn it first? This is bubble sort. Let's find out. In the last section, we saw something interesting. One passed through the list, and the biggest number floated to the end. But why does that always work? Let's break it down. Bubble sort has exactly one rule. Look at two neighbors. If the left one is bigger than the right one, swap them. That's it. Compare neighbors, swap if wrong. Do this for every pair, left to right. That's one pass. Here's what's beautiful about that simple rule. The largest number in the list will always win every comparison. It keeps getting swapped right again and again, until it reaches the end. After one pass, the biggest is locked. Guaranteed. After 2 passes, the 2 biggest are locked. After 3, 3. See the pattern? And here's the clever part. Each pass, the unsorted portion gets smaller. We don't need to check the numbers already locked at the end. Pass 1 checks 7 pairs, pass 2 checks 6, then 5, 4, 3, 2, 1. The work shrinks every time. But there's a catch. Big numbers move fast. They race to the end in a single pass. Computer scientists call them rabbits. Small numbers stuck at the wrong end. They only move 1 spot per pass. Those are the turtles, and turtles are the reason bubble sort is slow. One more thing. If you go through an entire pass and nothing swaps, the list is already sorted, you can stop. That's the optimized version. Add a flag. If no swaps happened, break. So 3 ideas make bubble sort work. Compare neighbors, shrink the window, stop if clean. We know the idea. Compare neighbors, swap if they're wrong. Now, let's write it down, line by line, no rush. First, we measure the list. N is just how many numbers we have. That tells the loops how far to walk. Then, the outer loop. This one counts the passes. I goes from 0 up to n-2. Each turn of this loop is 1 full walk down the list. Before each pass, we plant a little flag. Swapped equals false. We're being optimistic. We assume the list is already sorted, and we let the pass prove us wrong. Inside, the inner loop does the real walking. J steps through the pairs, 0, 1, 2, and look here, n-2 minus I, see the minus I. Every pass, the window gets shorter, because the end is already sorted. We don't touch it again. Now the one question the whole algorithm asks, is the left number bigger than the right one? If it is, swap them, and raise the flag, swapped equals true. We did some work, so the list wasn't sorted after all. After a full pass, we checked the flag. If nothing swapped, every pair was already in order. The list is sorted. So we break. We stop early. No wasted passes. That's the whole thing. 2 loops, 1 comparison, 1 flag. Alright, let's watch bubble sort run. Every single step. Nothing skipped, nothing rushed. Here's our list. 8 jumbled numbers. Pass 1. We compare the first pair, 6 and 5. 6 is bigger, so we swap. Now 6 and 3, swap. 6 and 1, swap. 6 and 8, 8 is bigger, so no swap. 8 and 7, swap. 8 and 2, swap. 8 and 4, swap. And 8 has reached the end. Our first number is locked. Pass 2. We go back to the left and walk again, 1 pair at a time. 5 and 3, swap. 5 and 1, swap. Then 5, 6, and 7 fall into line, and 7 locks into place. Pass 3. Again from the start, 3 and 1, swap. Then 3, 5, 6, and this time 6 settles home. Pass 4, a little shorter now. 1, 3, swap, 2 more pairs, and 5 clicks into place. Pass 5, just 3 pairs left. We nudge the last few, and 4 locks in. Pass 6, 1 final walk. Every pair is already in order, not a single swap. So we stop, sorted, every number home. That took 27 comparisons and 15 swaps. Bubble sort, one careful step at a time. We've sorted it by hand. Now, let's write the real thing. In Python. 10 lines, that's all bubble sort needs. Def bubble sort, taking our list. First n, the length. The outer loop, our passes. And before each pass, the flag. Swapped equals false. Stay optimistic. The inner loop walks the shrinking window. Compare 2 neighbors. And if the left one is bigger, swap them. Right there in one clean line. We swapped, so raise the flag. Swapped equals true. And after the pass, if the flag never went up, break. We're done. Now, let's run it. Line by line, exactly like the computer does. Watch the cursor. I is 0. The flag drops. We enter the inner loop. 6 and 5, swap. The flag jumps up. The array shifts. J moves on. Pass by pass, the green wall grows, and the watch on the right keeps the score. And here, the final pass. Nothing swaps. The flag stays down. Break, it stops itself. Now let's run it for real. Python bubble_sort.py. Sorted, 1 through 8. Real, running code. Same 3 ideas. Compare, swap, and stop when it's clean. So, how much work is bubble sort really doing? Our little list of 8 took 27 comparisons. But what about a big list? Look at the passes. 7 comparisons, then 6, then 5, all the way down to 1. Stack them up, and they make a triangle. Now here's the trick. That triangle is exactly half of a full square, n by n. For big numbers, we don't care about the half. What's left is n squared. Order n squared, and n squared grows fast. 8 items, 28 steps. 100 items, nearly 5,000. 1,000 items, 500,000. Double the list, and you quadruple the work. But it's not always this bad. If the list is already sorted, 1 clean pass, no swaps, the flag stays down, and we stop. That's order n, the best case. The worst case, a list in reverse, every single comparison swaps, full n squared. What about memory? No matter how big the list gets, bubble sort needs just a few extra variables. It sorts the list in place. That's order 1 space, almost free. One more quality, it's stable. Because we only swap when the left is strictly bigger, equal values never jump past each other. Their order is kept. So how does it stack up, stable, and great on nearly sorted data? But in practice, it's the slowest of the 3. Insertion sort does the same job with far less work. So that's bubble sort, the slowest sort you'll meet, and the simplest to understand, which is exactly why it's the most famous.